Hey folks, in this video we're going to learn how to interpret phase diagrams. So what we have here is a phase diagram for xenon, which shows along the vertical axis pressure and atmospheres, and temperature in degrees Celsius along the horizontal axis. The different regions of the phase diagram indicate what is the most stable phase at a given pressure and temperature. So this dark purple shaded region here means that if I have a pressure temperature in that region, the solid is the most stable phase. The lighter purple region here would be liquid, and then out here we have gas. So the first question is, what is the phase of xenon at room temperature and pressure? All right, well, certainly room pressure would be roughly 1 atmosphere. So 1 atmosphere would be along this dark purple shaded line. And the question is, where do we have the temperature? Now, we'll see that if we look at the horizontal axis here, the highest temperature is negative 105 degrees. So that actually means that if we continue with this line here, it's going to continue out way past the negative 105 degrees to reach room temperature, roughly 25 degrees. So we can see that clearly we're in a region where we have vapor. So that at room temperature and pressure, the most stable phase of xenon is a gas, which you probably would have guessed because we know that xenon is a noble gas, and so certainly at room temperature and pressure we would expect it to be a gas. Now let's look at part B. Part B is asking about the phase changes that a sample undergoes at negative 115 degrees Celsius. So here's negative 115 as it is compressed from 0.5 atmospheres to 25 atmospheres. So the first thing we need to do is figure out our starting point. So we see the intersection of the 0.5 atmosphere pressure and the negative 115 degree Celsius temperature is this point right here. All right, and clearly that means we are starting as a gas at that pressure. Now what happens as we increase the pressure? So let's just follow this line at negative 115 degrees Celsius up, corresponding to an increase in pressure. Follow it up. So first of all, we get to this boundary point here, and that boundary point we would probably say is roughly 0.6 atmospheres. So at 0.6 atmospheres, we might say that at that point we're converting the gas to liquid. So at negative 115 degrees Celsius and roughly again 0.6 atmospheres, and that's an estimate based on the curve that we have here because it's not marked off in a way that allows us to make a more precise determination of pressure. But at that point of intersection, it's roughly 0.6 atmospheres. So we're going to increase the pressure. We'll continue to increase the pressure. As it says here, we're going up to 25 atmospheres. So let's go ahead and continue to increase the pressure. So let's just continue up our curve until we reach this point here. And at that point, there, we're going to convert to solid. And so what pressure is that? So we can kind of estimate what that pressure would be in the same way. And we can see it falls roughly midway, maybe a little bit higher than midway between 0.5 and 1.0. So I'm going to say it's roughly 0.8 atmospheres. So at roughly 0.8 atmospheres, we're going to get a conversion of the liquid to the solid. And then, of course, as we continue to increase the pressure, nothing changes. We're entering into a region of solid and on up. So you're not going to expect to see any changes in phase, at least based on this phase diagram. Now, as we learned when we talked about water, for example, there can be multiple solid phases. There may be, at very high pressures, another phase of solid xenon, but we cannot tell that from this particular diagram here. We're certainly going to expect at 25 atmospheres it's going to be a solid. Whether it's the same solid phase that occurs at 1 atmosphere or not, we don't know. We need more information for that. So that's a basic interpretation of phase diagrams. Make sure if you have any questions, you let me know.